names. It's like it's going to be directed by Michael Bay and star Liam Neeson. Like I'm going to do the whole thing and like like an action movie poster with like big bold red headlines and.
Love it.
I might do a mock-up of that, like just for grins, So it's like
if you're giving a talk somewhere, yeah.
Oh yeah, people would eat that up for breakfast, and lunch, and dinner, and late night snack. But yeah, okay. So this particular faculty member is skeptical of anything that seems like remotely popular.
Oh really?
Like, probably one of the few people I know that actually prefers like charts and tables on slides. Yeah, I know, right?
Yeah, that seems so boring.
I know, right? Like, I understand like including them in the paper, but I think for the most part, like putting, especially like a full table on a slide, no, sir. It's, put the important stuff on the slide and like, okay, if you want the full details, look at the paper. That's what it's for.
Yeah, exactly. It's all about, like, talk should be about communicating ideas.
Yeah. See, that's what I think. But that's, but I think, and I guess I understand where they're coming from because, I think they're looking at it from like a credibility perspective. Like you have to show your credibility with like all these tables that you built in LaTeX. Which, I mean, okay, if that's what you're into, then I'm not going to judge, but it's not particularly my idea of a good time.
But that's kind of just another sort of status quo that you're dealing with.
Yeah. That's something I get from my mom when somebody tells me don't do something. That's just like, it's like, this bothers me. He's like, oh, does it? Let me do it 20 more times. Like when someone, like mom put a one of those pink flamingo things in her front yard, and somebody complained to her about it, and so she filled her front yard with them. She said, I thought they were complaining because the pink flamingo looked lonely.
That's great. I really respect that attitude. Tom just told me he's not going to be able to pair later, but that's probably good. Because he wants to go to bed early, and I want to go to bed early also.
Okay.
Let's see here. Tomorrow, I'm going to be at Discovery Park because I'm talking to Habib's class.
Oh, right. Yeah.
You
should come say hi.
Yeah.
If you can find my lab.
Well, I don't even know where the classroom is.
Okay. Well, yeah. I don't. Well, his. I assume they're in another part of the building, but
I think
most of the information science stuff is in a different wing from us.
D201.
Oh, D201. Okay, that's a common. All the departments use that. That's the big Mac lab or the big Mac classroom on the second floor.
I have no idea where it is or how Discovery Park is laid out.
Nobody knows how Discovery Park is laid out. It's classified. Seriously, like your first test as an engineer is being able to find everything you need to find at Discovery Park. How much of a cluster it is.
Right.
So when are you talking to the class? Like what time?
I think you said 3.
Oh, it's at 3:00? Okay.
I'm so amazed that there's not a map of Discovery Park on Google.
Yeah.
Or not amazed, but I'm disappointed.
Yeah.
Let's see. Map. This?
Kind
Center
of.
for Advanced Research.
I mean, there are signs when you get in too, like the D wing is here, and okay, so that's the E wing, that's material science. Um,
Oh, D. Okay, here's the D's. So I guess this is just first floor.
yeah, if the classroom number begins with a 1, then it's on the first floor.
Yeah. So it's probably above
So
this.
D201 is on the second floor. Actually, it's not the Mac. It's not the Mac classroom. It's one of the big. It's where my algorithms class was last semester, actually.
Oh, cool.
So it's kind of complicated to get to, actually. like even for people who know where everything is. So.
Great. Is there a second floor?
Like, because it's not accessible from the main hallways, basically. You have to go into this like side area, and the like you have to come in the back entrance because the front entrance to that classroom is usually locked. So.
Okay. Well, I guess I'll just try to get there early and call Habib.
Yeah, I would get there a little bit early.
Okay, well, we'll work on that. What room are you in?
My lab is in room F266. So basically, rather than have you try and find where that is, it's probably best if we like set a time and meet like in front of the computer science department office.
Okay.
Which is F201, and I can escort you through the labyrinth that is our wing of the building.
Yeah, that'd be super cool.
And
well,
I can show you the coffee cart and
yeah.
I can show you the espresso machine in our department. So.
Yeah, after this, I'm pretty sure I have your phone number, but if I don't, we should get that.
Let's see. Do I have yours?
I don't know.
Let's see. If I have yours, I can just text you. Oh, sorry, didn't mean to call you.
Oh, it's okay.
There we go. Keep it simple. You haven't changed numbers recently, have you?
I didn't
Otherwise,
get. Maybe I
otherwise,
have.
oh, have you?
Let me see.
Okay, somebody might have just gotten a very confused text message then.
Here, I'll text you.
Okay.
Oh, never mind. I got it. Yeah,
Oh,
I
you
did
got
have
it?
your number. Yeah.
Okay. Cool.
Okay. So, should we start digging?
We should.
Cool. So the last exercise we did was this the thing that you found the answer to
Yeah, the Qbert thing.
with the square iter.
Yeah.
So I copied it over to the Replit website.
Yeah.
And I guess there's this display function which I didn't know about, but
Yeah, me neither.
it just shows every step.
Yeah.
If we don't have that, then it still shows it though. I'm not sure why. I guess something's being returned. Oh, that's less than. Oh, because it's doing display guess right here.
Yeah.
Okay. So I think it would be good enough if we just talked through this code.
Okay.
A little bit, and then just give it a little bit of attention, but then
Yeah.
maybe go on and then come back to it
Yeah.
next week.
Yeah, that works for me.
Cool. So looks like we have a function definition,
Yes.
and then we have another function definition,
Right.
which is composed of, well, we have a guess and an x,
Right.
and then we're doing this.
Yeah, that's just basically that formula that was given in the problem.
Yeah. So we have like a 3-nested call expression.
Yeah.
So multiply the guess by 2. So you add together multiplying the guess times 2 with what's the divide, the quotient
Yeah.
of x,
Dividing x by the square of the guess.
I guess, and then adding those.
Yeah.
And dividing by 3.
Right.
So this improves.
Right. Well, yeah, it's similar to the thing we did for square roots, just a slightly different formula. Instead of taking the average of the two, we're doing something slightly different.
Mm-hmm. Then we have this cube root iter.
Right.
And in delta,
I think that's that author's version of good enough.
Oh, okay.
Because delta typically refers to like a change or a level of tolerance or something. So
right, amount of change in delta, and then this is the epsilon.
Right. Yeah, I was like, I thought delta was an odd choice, but yeah, it's basically it's their version of good enough.
Okay. Maybe I'll just change that to good enough because I think that's what it's called in the book.
Yes, it is.
Like we can name functions.
It's pretty sweet.
Pretty much anything. Like you can do that in JavaScript. You cannot.
Right. Yeah, that's true. You certainly couldn't do it in C.
So we ask, what is curve your iter? So this is kind of the meat of the algorithm.
Right.
Where it's checking if it's good enough. Well, it's checking if this is good enough, because good enough takes 2 guesses.
Well, no, it takes good enough takes yeah, that's again, I wouldn't have chosen those variable names.
Mm-hmm.
But because one is actually your target, right?
Right.
So
which is coming from
which is the number you're trying to your x basically.
Yeah. Oh yeah, okay. So what's the 1.0 here? What would that be called?
Well, that's just your initial guess.
That's the initial guess. Okay. Yeah, that makes sense. So if I make my initial guess 18,
then but there's probably I would guess there's probably mathematical reasons for starting at 1, because it's otherwise if you start with a different number it might not be guaranteed to converge. So
that makes sense. Well, it looks like Alexa got back to me.
Oh, yay.
Cool. So I think she's going to join in a little bit.
Cool.
Yeah. So good enough, guys. I don't know why. It's just like it's just slightly too much to understand everything that's going on. And I know this is a really small example.
No. This let's delve in. There's a lot going on here.
Yeah.
So, see, good enough takes two parameters, right?
Mm-hmm.
And so guess is the first. That gets bound to guess one, and then everything that's in the parentheses, the result of that is going to be your guess two. I say this like you can see me waving my mouse pointer or my pointer, and you totally can't.
I'm selecting him though.
Yeah. Okay. So you seem to be following along. So
yeah.
But that's what's going on here.
So yeah,
And so if it is good enough, then if it is good enough, then we return guess. Then otherwise you do. This is like the first bit of like procedural code that we've seen since we started this, basically. So.
Oh yeah. Okay. So this is the
true case, and then what follows is false. So.
Didn't we have names for the? Okay, so there's clauses.
Mm-hmm.
And do those. Well, that's for a condition.
There's a predicate, maybe? Is that the term it used? I can't remember. Yeah, I was going to say, I guess I could look at it, huh? There's an idea.
Oh, there's so many ifs.
Actually, because it started with cons, so it'll probably be a little quicker to. Oh, then clauses is what it's called. Yeah. Predicate is your condition, then clause, else clause. So.
Oh, yeah. Okay, so for an if statement, we get a predicate, consequent.
Right. Yeah. Consequent and alternative. Okay, there we go. That's the terminology.
Yeah. Just gonna do some live note taking.
Yeah, totally.
And so we return guess. If it passes this, if it's within 3 decimal places.
Right.
Or 1/1000. And then otherwise,
if it fails,
we print it. And I guess this is a new line function. Cool.
That would be my guess.
Yes. Yeah. And then we call this cube root iter. So this is the
and make the recursive call. Yeah.
And with our new guess, which is the result of calling improve guess, or improve with guess and x again.
Right.
And x. Then we check. It fails, so we do it again.
Right.
And is there anything? Should we?
I wonder if Scheme allows you to like turn on tracing. I know that's something Prolog helps you to do. That makes it a little less black magic-y. Because you can actually like trace when each function call is being invoked or exited or whatever.
Kind of like how Python Tutor has, like, it's the scopes and each call gets defined. You can step through.
Yeah, basically.
Do they support? No, they do Ruby, C, C++.
But no, I'm saying it might be built into Scheme. Like it's built into Prolog.
Oh, really?
There's that function, so like you can basically turn tracing on, and then every program you run will trace every step until you tell it to stop. So, in fact, I'm gonna to the Google.
Yeah, let's find that out. Alexa's having trouble signing up. said that was inside of an iframe. Got you. Amazingly.
Yeah. Yeah. So there's stuff about debugging in Scheme that looks a little bit complicated. Surprise, surprise. You can trace variables. So like that's probably the simplest thing to do is like trace, where is it? Does it say like where to do? Yeah, you just invoke it like you would any function trace, and then like a list of variables you want to trace.
Oh, but it's just variables.
No, you can trace other things too, but the syntax for it is more complicated. I posted a link in the chat.
Oh, nice. Cool. Oh, it's like the debugger. Interesting. Oh, what are the brackets?
Told you it was complicated.
I haven't seen that at all. Trace let trace. Trace lambda. Trace do. So I wonder if I can do it like here, maybe? Oh, unbound symbol trace. Maybe you do trace first. Something like that. That's a racket. Trace ID. Oh well. I will
Yeah, I probably have to like browse that in a little more depth some other time.
Yeah. That's really
But
cool.
It looks like it can be done. Wow, there's actually something that's simpler to do in Prolog than this. That's kind of amazing.
That is amazing.
Black magic, I'm telling you.
It definitely is. Well, I think we went through that function.
Yes.
Okay. Feel good about that. I'll go ahead and save this. We're guessing. Yeah, one of the cool things about REPL, you can save your sessions, and I can even like share them and save them, which is pretty cool.
Awesome.
Things in that. So you don't have to worry about spinning up a scheme instance.
That's good.
Okay, so you want to start reading at 1.1.8?
Sure.
Or were there more?
To get back to it, because we were looking at if stuff. So it's 1.1.8. Ah, never mind. I'm almost there anyway.
Yeah, pretty much. I think we answered all these questions last time.
Yeah. So Okay.
That was the last thing I remember.
Okay. Okay. Procedures as black box abstractions. There we go. Squirt is that's totally how I'm pronouncing it, by the way. Is our first example of a process defined by a set of mutually defined procedures. Notice that the definition of squirt iter is recursive. That is, the procedure is defined in terms of itself. The idea of being able to define a procedure in terms of itself may be disturbing. It may seem unclear how such a circular definition could make sense at all, much less specify a well-defined process to be carried out by a computer. This will be addressed more carefully in section 1.2. But first, let's consider some other important points illustrated, there we go, by the squirt example. Okay, it's not funny anymore. Observe that the problem of computing square roots breaks up naturally into a number of subproblems: how to tell whether a guess is good enough, how to improve a guess, and so on. Each of these tasks is accomplished by a separate procedure. The entire square root program can be viewed as a cluster of procedures shown in figure 1.2 that mirrors the decomposition of the problem into subproblems, which pretty much mirrors what we've been doing.
Mm-hmm.
The importance of this decomposition strategy is not simply that one is dividing the program into parts. After all, we could take any large program and divide it into parts, the first 10 lines, the next 10 lines, the next 10 lines, and so on. Rather, it is crucial that each procedure accomplishes an identifiable task that can be used as a module in defining other procedures. For example, when we define the good enough procedure in terms of square, we are able to regard the square procedure as a black box. We are not at that moment concerned with how the procedure computes its result, only with the fact that it computes the square. The details of how the square is computed can be suppressed to be considered at a later time. Indeed, as far as the good enough procedure is concerned, square is not quite a procedure, but rather an abstraction of a procedure, a so-called procedural abstraction. At this level of abstraction, any procedure that computes the square is equally good. Thus, considering only the values they return, the following two procedures for squaring a number should be indistinguishable. Each takes a numerical argument and produces the square of that number as the value. And so there's one version of square x that multiplies x by itself, and then there's one where there's a double procedure where you add x to itself, and then you take the exponent, the double of the log of x, and that will also get, and then this other thing with all these trig functions that I'm not even going to bother to parse out, but will apparently give you the result you're looking for. So a procedure definition should be able to suppress detail. The users of the procedure may not have written the procedure themselves, but may have obtained it from another programmer as a black box. A user should not need to know how the procedure is implemented in order to use it. Local names. One detail of a procedure's implementation that should not matter to the user of the procedure is the implementer's choice of names for the procedure's formal parameters. Thus, the following procedures should not be distinguishable. So defining square of x, multiplying x by itself, and defining square of y, and multiplying y by itself. This principle that the meaning of a procedure should be independent of the parameter names used by its author seems on the surface to be self-evident, but its consequences are profound. The simplest consequence is that the parameter names of a procedure must be local to the body of the procedure. For example, we used square in the definition of good enough in our square root procedure, as shown here. The intention of the author of good enough is to determine if the square of the first argument is within a given tolerance of the second argument. We see that the author of good enough used the name guess to the first argument and x to refer to the second argument. The argument of square is guess. If the author of square used x as above to refer to that argument, we see that the x in good enough must be a different x than the one in square. Running the procedure square must not affect the value of x that is used by good enough, because that value of x may be needed by good enough after square is done computing. It's getting into lambda calculus stuff. If the parameters were not local to the bodies of their respective procedures, then the parameter x in square could be confused with the parameter x in good enough, and the behavior of good enough would depend on which version of square we used. Thus, square would not be the black box we desired. A formal parameter of a procedure has a very special role in the procedure definition in that it doesn't matter what name the formal parameter has. Such a name is called a bound variable, and we say that the procedure definition binds its formal parameters. The meaning of a procedure definition is unchanged if a bound variable is consistently renamed throughout the definition. If a variable is not bound, we say that it is free. The set of expressions for which a binding defines a name is called the scope of that name. In a procedure, yeah, this is all of a sudden it got really deep in here.
Yeah. We got like 3 definitions right there.
Yeah. In a procedure definition, the bound variable is declared as the formal parameters of the procedure have the body of the procedure as their scope. In the definition of good enough above, guess and x are bound variables? Bound variables. But less than, minus, abs, and square are free. The meaning of good enough should be independent of the names we choose for guess and x, so long as they are distinct and different from less than, minus, abs, and square. If we renamed guess to abs, we would have introduced a bug by capturing the variable abs. It would have changed from free to bound. The meaning of good enough is not independent of the names of its free variables, however. It surely depends upon the fact, external to this definition, that the symbol abs names a procedure for computing the absolute value of a number. Good enough will compute a different function if we substitute cosine for abs in its definition. Okay. Internal definitions and block structure. We have one kind of name isolation available to us so far. The formal parameters of a procedure are local to the body of the procedure. The square root program illustrates another way in which we would like to control the use of names. The existing program consists of separate procedures. Okay, so this is the square root thing from previously. The problem with this, or well, maybe it's with a bug introduced. We'll see. The problem with this program is that the only procedure that is important to users of square root is square root. The other procedures, square rooted or good enough and improve, only clutter up their minds. They may not define any other procedure called good enough as part of another program to work together with the square root program because square root needs it. This problem is especially severe in the construction of large systems by many separate programmers. For example, in the construction of a large library of numerical procedures, many numerical functions are computed as successive approximations and thus might have procedures named good enough and improve as auxiliary procedures, aka helper functions. We would like to localize the sub-procedures, hiding them inside square root so that square root could coexist with other successive approximations, each having its own private good enough procedure. To make this possible, we allow a procedure to have internal definitions that are local to that procedure. For example, in the square root problem we can write, visual aid shown here, such nesting of definitions called block structure is basically the right solution to the simplest name packaging problem. But there is a better idea lurking here. In addition to internalizing the definitions of the auxiliary procedures, we can simplify them. Since x is bound in the definition of square root, the procedures good enough, improves, and square root iter, which are defined internally to square root, are in the scope of x. Thus, it is not necessary to pass x explicitly to each of these procedures. Instead, we allow x to be a free variable in the internal definitions as shown below. Then x gets its value from the argument with which the enclosing procedure square root is called. This discipline is called lexical scoping.
Wow.
Yeah, this is a lot.
Yeah. And that's where JavaScript gets this from Scheme.
Right. Or just so you have functional languages in general. So.
And we have a footnote here.
Yeah. So we also have one more paragraph. So okay. I'll get to that in a sec. Cool. So we. Okay. So yeah, I'll go ahead and read the foot. Lexical scoping dictates that free variables in a procedure are taken to refer to bindings made by enclosing procedure definitions. That is, they are looked up in the environment in which the procedure was defined. Sounds a lot like JavaScript closures, actually.
Yeah.
We will see how this works in detail in Chapter 3 when we study environments and the detailed behavior of the interpreter. Okay, so last paragraph. We will use block structure extensively to help us break up large programs into tractable pieces. Footnote. Embedded definitions must come first in a procedure body. The management is not responsible for the consequences of running programs that intertwine definition and use. Okay. The idea of block structure originated with the programming language ALGOL 60. It appears in most advanced programming languages and is an important tool for helping to organize the construction of large programs. Phew.
Nice. That's good. So there's probably a design pattern that we could say is going on in that last example.
Yes.
Obviously, there's closure.
Yeah.
What design pattern?
Let's see. I don't know like what you would call it. I'd like. Are you talking about like the helper functions part or auxiliary functions, whatever you want to call them?
Yeah.
I'd say probably auxiliary functions, but I don't know if that's like, is that considered a pattern per se? Maybe it is.
I don't know all. I don't know very many.
I'm not sure there's like a canonical definition of what constitutes a pattern.
Yeah.
That's probably a whole nother ball of wax.
Yeah. It sounded a little bit earlier when they were talking about bounded free variables. That was I was thinking of global and local scope and wanting like favoring not binding variables.
Yeah, that's part of that all that has its roots in lambda calculus, basically.
Cool. I just started reading.
I'm sure we will talk about more.
Yeah. That's a really neat book to read alongside this. I started on the intro to functional programming through lambda calculus.
Oh, that's right. Yeah, you told me about that.
Yeah, immediately. I mean, in the introduction, I was talking about just all the same things from this chapter.
Yeah.
Regular order and applicative order.
Right. And because lambda calculus is actually quite old.
Oh yeah.
Yeah, it has its origins in like the 30s.
Yeah, Alonzo Church.
Right. Yeah, because it's interesting because lambda calculus and the Turing machine were independently developed at around the same time and for generally the same purpose. They just came up with very different approaches, but they're actually computationally equivalent. Like anything you can do with a Turing machine, you can do with lambda calculus and vice versa.
Yeah.
Now some things are easier to do in one framework than the other.
Right.
But you can do both. So and both of those were their respective creators' attempts to make sense of Gödel's incompleteness theorems.
So did the halting problem come specifically out of the Turing machine?
It might have. I'm actually not as familiar with the history of that problem. Yeah.
Well, I think that
it seems logical. Okay, yeah. So Alan Turing proved in 1936 that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. So probably.
Yeah, and those were both from. Was it Boltzmann? It wasn't. Who came up with the halting problem?
Let's see. The term says the term came from Martin Davis. I have no idea who that is, but
oh, okay, that's older.
Maybe I should.
I thought it was Turing's advisor.
Well, Turing came up with the concept, but maybe he didn't call it that.
Okay. Because I think there was. Oh yeah, piano axioms. That comes up in this.
Oh yeah. Freaking Pinot axioms.
Yeah, or Pinot.
Yeah. I'm told that's how it's generally pronounced in America. That's actually how my real analysis professor pronounced it. So.
Oh, Minsky's on here.
Yeah, that's. I think because I took real analysis. Not sure why, but I took real analysis, and one of the most difficult things I've ever had to do in my life was prove like basic properties of arithmetic using just a few of the we couldn't even use all of them. We had to use like there were like 5 basic ones, and we had to like use them to prove like the commutative property of addition and that any number plus 0 is still 0. And all that kind of stuff. So
That's pretty cool, though.
it is cool. Like I felt a really strong sense of accomplishment once I did it for sure. But doing it was like, oh my god.
Yeah. No, that's intense. That's very.
I see why math majors are a special breed.
Indeed. This is a pretty nice wiki. I think there was one footnote that we skipped over earlier.
Oh, was there? Okay, let me check. Let's see. 20,
I might be wrong.
oh yeah, I think I did. Yeah, number 26. Yeah, the concept of consistent renaming is actually subtle and difficult to define formally. Famous logicians have made embarrassing errors here. Name some names. Come on.
Yeah. I don't want to give any names.
Right? I'm assuming that probably if you search, you can find out what they're talking about. That's probably why they don't tell you. It's like, no, you got to find this out for yourself.
Yeah, cool. Okay, so we got this factory thing or whatever this is. Where, as far as I know, nothing global is being redefined, so it's kind of an arbitrary example, but it is showing that we get plot scoping with scheme or lexical scoping, but then it's called a block.
And
Cool. I'm opening 1.2.
woohoo!
I'll close this. Got that saved.
Okay. PDF of latest survey papers out the door.
Oh, awesome. Congrats.
So, well, not like submitted for public. This is to like go to Dr. Bryant, to the department chair, to look at. Well, he's one of the authors on it. So.
Oh, cool.
But he had been kind of putting off his review of it because Dr. Doe, the other faculty member who's working on it, has been like obsessing over like every little thing, which is probably a good thing, but can get annoying sometimes.
The guy who loves slides.
No, this is a different one.
Oh, okay.
No, Dr. Doe is just like super detailed.
Gotcha. Well, it's good. It's good you have detailed eyes looking.
Yeah, that's the thing. You know, she will not let me make a fool of myself in public. So there's that, I guess.
So, oh, nice. I'll start reading here at 1.2.
Okay.
Ready?
Ready.
Okay, cool. Actually, Danielle, do you mind muting your input? I mean, you'll have to like mute and unmute to talk to do this, but I hear myself and I see you've already done it because I can't hear myself now. Thank you. Open the chat. Okay. Procedures and the processes they generate. We have now considered the elements of programming. We have used primitive arithmetic operations. We have combined these operations, and we have abstracted these composite operations by defining them as compound procedures. But that is not enough to enable us to say that we know how to program. Our situation is analogous to that of someone who has learned the rules of how the pieces move in chess, but knows nothing of typical openings, tactics, or strategy. Like the novice chess player, we don't yet know the common patterns of usage in this domain. We lack the knowledge of which moves are worth making aka which procedures are worth defining. We lack the experience to predict the consequences of making a move or executing a procedure. The ability to visualize the consequences of the actions under consideration is crucial to becoming an expert programmer, just as it is in any synthetic creative activity. In becoming an expert photographer, for example, one must learn how to look at a scene and know how dark each region will appear on a print for each possible choice of exposure and development conditions. Only then can one reason backward, planning, framing, lighting, and exposure, and development to obtain the desired effects. So it is with programming, where we are planning the course of action to be taken by a process, and where we control the process by means of a program. To become experts, we must learn to visualize the processes generated by various types of procedures. Only after we have developed such a skill can we learn to reliably construct programs that exhibit the desired behavior. A procedure is a pattern for the local evolution of a computational process. It specifies how each stage of the process is built upon the previous stage. We would like to be able to make statements about the overall or global behavior of a process whose local evolution has been specified by a procedure. This is very difficult to do in general, but we can at least try to describe some typical patterns of process evolution. In this section, we will examine some common shapes for processes generated by simple procedures. We will also investigate the rates at which these processes consume the important computational resources of time and space. The procedures we will consider are very simple. Their role is like that played by test patterns in photography, as oversimplified prototypical patterns rather than practical examples in their own right. Linear recursion and iteration. We begin by considering the factorial function defined by in bang, which typically means factorial, is equal to n times n minus 1 times n minus 2, etc., up to n. There are many ways to compute factorials. One way is to make use of the observation that n factorial is equal to n times n minus 1 factorial for any positive integer n. N equals n times n factorial times n minus 1, or that for up to n minus 1. Thus, we can compute n factorial by computing the factorial of n minus 1 and multiplying the result by n. If we add the stipulation that 1 factorial is equal to 1, this observation translates directly into a procedure. Factorial of n, if n equals 1, is 1. Otherwise, it's the product of n and the factorial of n minus 1. We can use the substitution model from section 1.1.5 to watch this procedure in action, computing 6 factorial as shown in figure 1.3. And we get this nice nose shape of procedures called a linear recursive process for computing factorial of 6. So we take the factorial of 6 and then we multiply that by the factorial of n minus 1 times factorial of n minus 1 times factorial until we get to 1. And then it goes backwards. Because we're no longer calling factorial at that point, we're just evaluating. Now let's take a different perspective on computing factorials. We could describe a role for computing in factorial by specifying that we first multiply 1 by 2, then multiply the result by 3, then by 4, and so on until we reach n. More formally, we maintain a running product together with a counter that counts from 1 up to n. We can describe the computation by saying that the counter and the product simultaneously change from one step to the next according to the rule product. I'm not sure how to say this backward arrow.
I would just say is defined as or something like that.
Oh, okay. Product is defined as the counter times product. And the counter, oh, I guess this is the value of these things each time that the procedure runs.
Right.
Okay. So product is counter times product, and the counter is the counter plus 1, so it's just incrementing. And stipulating that n factorial is the value of the product when the counter exceeds n. So this
Just
feels
tail
like
recursion, basically.
Oh, okay. Cool. I didn't know that. Once again, we can recast our description as the procedure for computing factorials. And we got a footnote. In a real program, we would probably use the block structure introduced in the last section to hide the definition of fact iter. Define factorial in. We define iter, which takes a product and a counter, and if the counter is greater than n, we just return the product because we've exceeded. Otherwise, we call iter again. What's the first thing going to be? Oh, okay. We call iter again with the product being the counter times the product, and then the counter being the counter plus 1. And then we have this iter 1, 1. So we're saying this is using the block structure because we have this inner function called iter, which isn't available outside of factorial.
Right.
And we avoid doing this here so as to minimize the number of things to think about at once. It's always good. Okay, so counterpose this shape, an example of doing the recursive factorial with this shape. As before, we can use the substitution model to visualize the process of computing 6 factorial as shown in figure 1.4. Oh, I guess we should. So I think this is the actual example, which is the same except for fact iter, it's taking a max count.
Well, remember the previous program was expanding and contracting. This one maintains the same amount of space every time.
So what's this last? Oh, max count is just, that's the thing that you're calculating.
Right.
Okay. Oh, yeah. Okay, and it starts at 1. The product and the counter start at 1. Interesting. So we still get 720, but in this case, it's quite a few less computations to find our answer.
Well, it's the same number of computations, but you're using less memory at a time, because one of the risks of doing just naive recursion in the previous one is if you're computing some function of a very large n, if you have a lot of calls, you risk running out of memory.
That makes sense.
Whereas this takes, the same amount, relatively small amount of space each time. Both actually do the same number of computations. It's just a matter of how they're allocated.
Oh, interesting. Okay. So I guess this is doing 8.
Because okay, so let's scroll back up for a second to the previous one, the nose one, as you pointed out. So it's got that, so it makes that first call for factorial 6, and so it's it's building it basically puts per the function definition, it has to make another recursive call, so it basically puts it pushes down factorial 6 on the stack and then brings in factorial 5, and then when you still have to call, and so you keep having to put things on the stack until you reach your base case, and then you pop the stack until you're done. But again, like I said, if you have a very large n, you could run out of memory.
Yeah, potentially really easily.
Whereas with this approach, that's much less of a risk.
And this is called tail recursion?
Yes.
Interesting. Okay. So you're keeping track of is the 6 the tail?